Good afternoon. We will continue today with a bunch of applications related to vector functions. In particular, vector functions which represent a motion in space along a curve, along a space curve. And the first topics, as you can see from the title, we're going to cover a bunch of topics here. The first one is, in fact, a spin-off from Calculus 1. You will see immediately what I'm talking about. How do we compute the arc length, the length of a curve in space, a 3D curve? It's something we did in Calculus 1 for a planar curve, right? So for for the graph of a function, in other words. So the tool we're going to have at our disposal to achieve the same thing is obviously more general because it's a 3D curve, not necessarily given by single variable function, obviously, right? Because it's a three-dimensional curve, but the principle is the same. I should mention at this point that from now on you will see lots of types of integrals that are set up to measure a certain thing. And remember, those of you who take my class with me, that you're supposed to update that formula sheet along the way, maybe remove some of the things that you memorized already just to not have too much clutter. Like, for example, at this point you should know by memory, right? I mean, things like dot product or how to compute the magnitude of a vector. This probably should not be in the formula sheet, but as we move along with new formulas or integrals, the setup of those integrals and other related formulas, you should make sure you put them in the formula sheet. So how do we compute the arc length, also known as the length of a curve, between 2 points on the curve, right? So let's say, take the time obviously to sketch this graph, but let's say we have a curve given by a vector function r of t. We're not going to need actually its components to set up the formula, but remember this, if you write it in the component form, it'll have three component functions. And let's say that t is restricted in a closed interval ab, so that we can have actually a curve with a finite length. And so the goal or the question is, what is the length of the curve if t varies between a and b, right? As t goes from a to b. So now remember, for every point t, for every value of t, you have a position vector. So over here, this is your starting point on the curve that I'm going to emphasize here, and then r of b is the endpoint on the curve. As with all the integrals designed to measure these concepts, I mean these quantities, you begin basically by setting up a partition of the domain. I want to also make a remark here that I'm not going to get into the definition to the level of the detail that we had when we studied the Riemann integral for the first time. So let me actually write it as a remark here. I'm going to get back to this in a later lesson, maybe when we study the double integral later. I'm going to assume that you remember how we set up the basic Riemann integral in Calculus 1. Like the whole concept, right? I mean, remember, so we're going to assume knowledge of it, so that I can actually refer back to the procedure of defining and computing the Riemann integral in fewer words. I don't want to get too much into detail, so that I won't do the whole detailed discussion for every single integral, yeah. But remember, the whole idea is to actually partition the domain to create what is called a Riemann sum, and then basically evaluate either the function or something related to that function at intermediate points on this partition. So if I take, for example, a typical partition xi plus 1 picks an intermediate point, let's call it ci, and then the Riemann sum is basically a summation, just for the basic Riemann integral, of the function evaluated at that intermediate point times the distance, I mean the length of that segment in the partition, xi plus 1 minus xi, where I goes from 1 to n. Now, 1 to n minus 1, if I have to be correct, right? Because it ends with xn. Typically, I should say here, I mean, usually, yeah, in my notation here, x naught should stand for a, xn should stand for the endpoint b. So that means the way I wrote it here should be like from 0 to n minus 1. Now, when you set up integrals to compute other quantities, like in this case the arc length, what's different in addition is what function you evaluate at the intermediate point. So this could be different depending on the context. Like for example, if we design the integral to compute a volume, that's going to be a slightly different format. Here as well, you're not going to evaluate the actual function, you're going to evaluate a different piece that actually is designed to compute the length of the curve. So it depends on the object at hand, right? But all Riemann integrals are set up, roughly speaking, in this manner, right? So a partition of the domain, then you multiply the measure of each piece in the partition, that is to say, in this case, the length of that interval in the partition, and some stuff evaluated at an intermediate point in the partition, whether it is the function itself or something related to that function, again, depending on the context. So, sorry, I'm a little bit too vague right now, but you will see later on, we're going to have this principle repeated all over again as we move on with different types of integrals. We're going to have integrals to compute, for example, center of mass, surface integrals, double integrals, triple integrals, and so on and so forth. And the principle is the same. The shape of the domain will be different, and what we evaluate the function on, again, is going to be different. So going back to the arc length, the domain is from A to B, and if we assume, just like in calculus 1, that we're going to make a partition, then for each point in the partition, so let's say this is T1, T2, somewhere here in the middle, Ti, Ti plus 1, all the way to B, right? So usually remember, in the standard notation, A corresponds to T naught, B corresponds to Tn. So for each of these intermediate time points, you're going to have some intermediate points on the curve. And of course, you're going to have position vectors at each of these points. So for example, let's do this with a different color so we can emphasize it here. For example, let's say this one over here with green. These vectors, let's say, correspond to R of Ti and then R of Ti plus 1. We can approximate, the idea is that we can approximate the length of the curve if we connect these intermediate points on the curve with straight lines. So in other words, we're going to approximate the length of the curve with secant lines. And we did this in calculus 1, I want to remind you, except that we did it in the context of a single variable function. So in this case, if I were to set up the Riemann sum to approximate the length of the curve, that should be basically the sum of the length of each secant line, or secant segment if you want, that connects those intermediate points. But remember vector operations, right? So again, let's zoom out a little bit here so you can see the picture. If I were to zoom out here in the middle, what you have is the curve, right? You have R of Ti, you have here R of Ti plus 1. The actual secant line, if you write it as a vector, it's nothing but the difference of R of Ti plus 1 and R of Ti. Now I'm interested, of course, in the length of the curve. I'm trying to approximate the length of the curve. So of course, in the Riemann sum, I'm going to have to add the magnitude of this difference of these two vectors. All right, so when you set up the Riemann sum that approximates the integral to compute the length of the curve, you're going to have some summation of the magnitude of this difference times, of course, the distance on a segment on that partition, ti plus 1 minus ti. Provided, of course, this Riemann sum has a limit, this is going to converge as n goes to infinity, right? If you make finer and finer partitions, this is going to converge to the integral from a to b r prime of t magnitude of r prime of t dt. Why? Because as n goes to infinity, the secant line is going to be approximated by the tangent vector. Right, as n goes to infinity, you have finer and finer partitions. Those 2 points in the partition come closer and closer together, and then that's going to be approximated by the tangent vector, r prime of t at that point t. Ti plus t minus ti can be, of course, approximated by dt as n goes to infinity. So as a formula, the arc length is going to be given by the integral from a to b, magnitude of the tangent vector r prime of t dt. All right, so later on, I'm gonna write the summation of these Riemann sums. I'll probably do it one more time for the double integral, but then later on, I'll just basically emphasize the approximating piece in the actual integral, right? So basically, I'm gonna go directly to setting up the stuff inside the integral over here, in the picture at least, right? Assuming that you guys realize that this comes actually from the limit of a Riemann sum, because that's just faster and it's good enough actually for most of the integrals we're gonna discuss later. Now, of course, alternatively, you can just simply write down the formula and not bother on how you actually obtain it. But I don't think that's wise. You should have just a basic understanding how that integral comes to be. Again, you don't have to go from a very detailed Riemann sum. But whenever you set up a new tool that is given by an integral, at the very least, you have to visualize a partition and what you actually add up in that partition. That's the key thing, okay? So in this case, what we're adding up is the magnitude of the tangent. Why? Because again, if I start approximating the length of the curve with secant lines, as I make that partition, the number of points in the partition as it goes to infinity, all of those secant lines will be approximated by tangent vectors. So the magnitude of that difference is going to become the magnitude of the tangent. Before we move on to an example on the second page, I want to point out that in Calculus 1, Calculus 2. In Calculus 2, you found the length of the graph of a function, right? So let's say you have a single variable function between a and b, y equals f of x, right? And then the length was the integral from a to b. If you remember, the square root of 1 plus f prime of x squared dx. So I want to point out that this is nothing but the same formula, but in a more particular way, right? I mean, this square root is nothing but the magnitude of the tangent vector, except that in Calculus 2, you can view your function as a vector function with components x, f of x. That's the only difference. I hope you see what I'm talking about, right? So I mean, the formula here with r prime of t, of course, is more general. The formula in Calculus 2 is more particular, right? Because again, you have an explicit function of a single variable. You can still view it as a vector function with components x, f of x. And of course, in that case, the tangent vector will be 1 f prime of x, right? The derivative of x is 1. And the magnitude of the tangent vector will be square root of 1 plus f prime of x squared. And that's the stuff you integrate. I find it very useful to put things in the context as we move along with more general stuff, because you will see some of the stuff you learned earlier are just particular cases of more general tools. All right, so let's move on to the second page with an example. All right, so one thing I want to mention before we go over a couple of examples, that's also kind of important, it's at least the way I teach the class. For all of these integrals, we have something called a formal notation, what I like to call it a formal notation, and the actual way to compute that integral. Formal notations is when we need a general notation for a formula without getting into the specifics of things like what the domain is for that function and so on and so forth. And ds with small s here usually denotes it's a formal notation for the arc length. And you'll notice also in many books the same thing, right? The formal notation always on the left side, again, it's just like the name implies, it's just a signal that the tool involves an integral, and it'll have basically some notation inside that it will suggest the way to set it up, again, before you know what the function is actually equal to. So again, ds being the arc length element, typically it's a notation of the element of the piece of the curve. So you integrate over pieces of those curves, right? So that's like a formal notation for that piece in the Riemann sum. And on the right hand side, you actually write how you set up the integral, how you compute it. In the case when you have, again, a vector function r of t with the domain a and b. And you're going to see this pattern throughout the class, right? So formal notation, and then on the right hand side, setup of that integral, which is of course the important part. But the formal notation is also useful because it's like a shortcut, like a general shortcut for the tool at hand. So let's start with a very simple example. I like sometimes to start with an example that you could actually compute by other means. So let's say I have a two-dimensional curve given by the components cosine of t, sine of t, and I want t between 0 and pi over 2. And I want to compute its length. So we can just set up the integral directly. Sometimes you may prefer to compute r prime separately, but in this case it's just easy enough to set it up directly. Of course, you need to do the derivative of the vector function first. So r prime is minus sine of t cosine of t. We're going to take the magnitude and then integrate. Magnitude is square root of minus sine squared, minus goes away, cosine squared dt, and this is maybe even too easy to begin with, right? This becomes the integral of 1 dt, because sine squared plus cosine squared is 1, so that's the integral of 1 dt. So arc length becomes an old-fashioned calculus 1 integral. Integral of 1 is t between pi over 2 and 0. Answer is pi over 2. Of course, if you look carefully at the curve, you realize that that's not a surprise. Cosine sine of t are the coordinates of the unit circle, are the polar coordinates actually. If you remember polar coordinates, any point on the unit circle will have the x coordinate given by the cosine and then the y coordinate by sine of t. As t moves from 0 to pi over 2, that gives you just a quarter of a circle. And the area of the full circle of radius 1 is pi. Excuse me, not the area. The length of the full circle is 2 pi. A quarter of it, of course, is 2 pi over 4, which is pi over 2. So this is an example in which, of course, you don't need to do the integral. We just did it as practice to confirm. Don't forget that often you may not need to employ more complicated or general tool if the same answer can be found more directly. So always be aware of this aspect. We're not going to focus on these aspects because we learn Calculus 3, so we can learn the examples for which Calculus 3 tools are necessary, but don't get into the tendency, which is common later, to use a complicated tool when an easier solution is at hand. So let's do one non-trivial example. Let's say I have a curve given by the components 1t squared t third and t between 0 and 1. Whenever I want to save some time in class, 0, 1 is practically the default domain. It tends to be the one that gives you fewer tedious computations in most contexts, depending on the case. All right, so what's the length of it? Let's compute separately r prime of t. Derivative of 1 is 0, then 2t, then 3t squared. We're going to have to integrate over the magnitude of this. So the integral from 0 to 1, magnitude of r prime, that's the square root of 0 squared plus 4t squared plus 9t fourth dt. Now, when I teach this class, I usually don't go into fancy integral methods, integration methods. I mean, because it's kind of detracting a little bit from focusing on the main topics here, but always remember that the basic, the most, let's say the most useful or the most encountered methods, like the U substitution or by parts, these are usually fair game in my quizzes or exams because they happen often, and you should try these if the integral is not immediate. Typically, I don't give in tests, something that may require, for example, trigonometric substitution or something more complicated than that. Maybe you may have to do a rational partial fraction decomposition, but nothing too complicated, so nothing that requires, finding lots of coefficients and things like that. You do, however, have to be creative once in a while, in the sense that, for example, you may have to do some algebra manipulations. The way if you look at this problem here, it doesn't look like it can do it immediately, and it's not obvious which method may work. But at the very least, try to manipulate it algebraically, and then maybe an idea may pop up. So one thing you could do, you notice that you have t squared and t fourth, so we could actually pull out t squared from the those two terms, and then we can pull t squared out of the radical. T is positive, it's in between 0 and 1. And if I write it like that, it should be pretty obvious now that a U substitution is the way to go. Might be a good idea to stop the video now and try to finish this integral yourself. Just perform a U substitution. Why does it work as U substitution? Well, because if you pick your substitution for 4 plus 9t squared, du, the derivative of it is 18t dt, which pairs nicely with the remaining t dt outside of the integral. All right, let's change the bounds as well. If t equals 0, u, look back to the substitution over here, u is going to be 4. And if t equals 1, u is 13. So the new integral now is from 4 to 13 square root of u, and then from the substitution of du, t dt becomes du over 18. 1 over 18, u to the 1/2, and then the power rule, 1/2 plus 1 is 3/2, so I'm going to have 2/3 u to the 3/2 from between 4 and 13. Usually we don't have a nice formula for these you don't expect to have a nice number when you're done with it. So in this case, it's going to be 1 over 27 times 13 to 3/2 minus 4 to the 3 halves. I usually don't bother to simplify it further. Be aware that in back of the books, sometimes you are given these quantities as like 13 square root of 13. This becomes square root of 4 to the third. That's like 8. Square root of 4 to the 3. Yeah, but you don't have to. I'm just making you aware that you may see the same answer in a different form, in a different simplified form. So this is the length of the curve. This is how you find the length of the curve, right? So roughly, to summarize, you integrate over the magnitude of the tangent vector. So let's move on with the next topic. I think I'm going to fit its definition on the same page. We're going to talk about another interesting or important quantity which is related to motions in space, namely the curvature. So let's see what this concept is all about, what it tries to measure, and how do we define it. So remember, the tangent vector gives you the speed and gives you how fast you go and where you go, basically, right? So I mean, as the motion evolves on the path here, there are essentially two quantities that are blended together in that vector, right? The change in the direction and change in the speed, basically, the magnitude of the vector. The problem is that, I mean, it's not the problem. The idea is that often you want to be focused on a specific aspect of it. Maybe sometimes you want to be focused on measure how much, for example, the motion changes direction, at least compared to the overall motion in space. That might be important. I give you sometimes these motivations in class. In aviation, for instance, or other applications like this. For instance, there might be some restrictions in the mobile, in the airplane, for example, in the sense that it cannot take, for instance, turns sharper than a certain degree, right? So, or you want to, for example, measure how much drift there is, for instance, if you want to go over a certain path and then you want to minimize, for instance, the amount of turning compared to the distance traveled. Maybe for a certain distance traveled, there is a certain allowance of how much turning due to drift may happen. So anyway, this is another way of saying, to formalize this question, is that the curvature is a scalar. So let's write it actually in green here. The curvature is a scalar, because that's like a definition. So it's a scalar that measures how much the curve turns relative to the length of the curve. So it's like an intuitive definition, but the idea is to have a scalar quantity that measures at each point. It's important here to point out this is a point property. It's a local property at a point. So in other words, as you move along the curve, the curvature itself changes its value, may change its value depending on the case. But again, we try to put it in a number, in a scalar, a quantity that essentially measures how much turning happens in the curve as you move along the curve with respect to the distance traveled on that curve. Now, remember from the previous lesson that we have something called the unit tangent, which is a vector, and as the name implies, it's basically the tangent vector normalized, that is scalar multiple by 1 over its magnitude to make it of length 1. Unit tangent just gives you the direction of motion, right? Irrespective of the speed. By dividing, remember the magnitude of r prime is the speed, right? So you divide the tangent vector which is a vector, over the speed, right? So you basically disregard the magnitude of r prime, and you just leave the information that relates to the direction of motion, right? The unit tangent tells you where the motion goes, in which direction along the curve. So therefore, what do you think then t prime of t will measure? Well, t prime of t is going to be the change in that direction. Now be aware that while the unit tangent is, as the name implies, of length 1, the t prime of t is not going to be obviously 1, at least not necessarily, right? So the t prime of t can have any value whatsoever, any magnitude, right? I mean, it could be 0 if there is no change in the direction, could be a big number if it's a lot of change, right, in the direction itself. So again, t prime of t is going to measure the change in direction, or the turn if you want. And I want to compare this to around that point. If I take a tiny interval around that point t, I want to compare it with how much distance is traveled around that point. Now remember, around that point the distance traveled is approximated by the magnitude of the tangent, right? We're talking about, again, on the curve, what happens nearby a point t. T prime of t changes in direction at that point, magnitude of r prime of t, how much is traveled at that point, right? In other words, the speed, if you go back to the analogy of the mobile on the curve. So if I want to compare the two, remember, look at how I define the curvature. Obviously, the curvature, which is denoted by k of t, just to keep up the notation in the book, it doesn't have to be k, but so the curvature denoted by k of t is going to be just the ratio between the magnitude of the t prime of t over the magnitude of r prime of t. So I hope it makes sense. I'm going to repeat the formula on the next page. There is another version of how an alternative way to compute it, but I hope it makes sense. Again, keep in mind the meaning of these vectors, right? T prime, how fast you turn or how much you turn, compared, that is to say, divided to how much travel happened on that curve. So for example, a low curvature would means very little turning with respect to the distance traveled. I'll show you a quick example with a little figure on the next page. So let's stay tuned for the next page. All right, so that's the formula for the curvature. I'm not going to prove this, but there is an alternative way to compute it. Which one you use, it's up to you, but usually there is an obvious way which one is more preferable. I'll talk about in a moment. Another one, which is just in terms of derivatives of r. So another way to compute this will be on the top the magnitude of the cross product of r prime of t and r double prime of t over the magnitude of r prime of t third. In pretty much any calculus book, you'll see the proof of this formula. Obviously, which one you're going to use, it depends on the type of function. For example, if derivatives become much easier to compute, if the function becomes easier via differentiation, probably you may want to use the second version. The first one is more preferable, especially if you have to compute the unit tangent anyway, depending on the problem. But let's make sure, before we come up with examples, make sure we understand the concepts of what's a low curvature, what's a high curvature. So suppose, for example, the motion looks like this. If I look at the point here, let's say this corresponds to the point t equals a, right? Let's say this is the graph of r of t. If you look at the curve here, it's so smooth, there is very little turning compared to the distance traveled. So if I take a tiny interval around this point, a point t equals a, how much the curve turns is very little in comparison to how much is traveled. So I would expect the curvature to be low on this point. On the other hand, if I look at this point, let's say this corresponds to t equals b, it's a very sharp turn, right? So if I approximate that point with a tangent, there is a lot of turning, so I would expect the numerator, t prime of t, to be a bigger quantity, the magnitude of t prime, because it's a lot of turning in a short distance. So I would expect k of b to be larger here. Guess what? What is the curvature if I move on a straight line? Try to answer that question. Right? So it should be 0. There is no turning. Right? There's no turning on the line. It's a straight line, so the curvature should be 0. I don't have to compute it. What about a full circle? Can we say something about the curvature? Well, we have to compute it, but one thing I can tell you for sure, that's going to be a constant. It's a full circle. There's the same amount of turn compared to the distance traveled, no matter where I am in the circle. All right. With that in mind, let's come up with an actual example. Here's an example in which, let me see. Let's see which one I'm going to use first. Yeah, let's do an example that will use the first part of the formula. So let's say I have r of t given by sine of t, cosine of t, t squared over 2. We don't even have to sketch it. Let's say the question here is to find the unit tangent. Actually, let me think a little bit here. I'm trying to think about, no, sorry about that. I don't want this one, t, just t, because then I'll have a, yeah, so another example. I'm going to show you some examples with maple. It can be quite tedious depending on the function at hand. When you differentiate t, the unit tangent, that's when things can get ugly on paper. So let's choose r of t, sine of t, cosine of t, and t. Okay. And let's find the curvature. I'm going to specify the point later, but let's just plug in the point later. I mean, curvature at the point t, I'm going to say something about that t in a moment. So let's do the unit tangent first. Obviously, we need to compute the derivative. So that's going to be cosine of t minus sine of t and 1. In order to find the unit tangent, which is r prime over the magnitude of r prime, I'm going to have to compute the magnitude, obviously. So the vector cosine t minus sine t and 1 is scalar multiple to 1 over the magnitude of this. See, this is where I can tweak the function to make it easy when I give quizzes in class, because later on I'm going to have to differentiate this mess again to find t prime, right? And if the denominator is still depending on t, that can be a little bit tedious by hand. Now, the denominator in this case doesn't depend on t because it so happens that the cosine squared plus sine squared is 1, so this is going to be just 1 over root 2. So the unit tangent is 1 over root 2 cosine minus sine and 1. You can leave the scalar out or bring it inside, it's up to you, doesn't matter. Just make sure you don't do the operations correctly. And moving on, we need now the magnitude of t prime. In fact, at this point, probably we can just set up the curvature right away. On the top is the, look at the formula on the top here, right? On the top is the magnitude of t prime. So we're going to have to differentiate t prime. So on the top is the magnitude of the derivative of t. That's 1 over root 2 derivative of that, which is minus sine of t minus cosine of t and 0. divided by the magnitude of r prime. Let's look at r prime here. That's going to be square root. We did that before, but let's do it again. Square root of cosine squared plus sine squared plus 1. We can pull the scalar on the top out, and then the magnitude of the remaining vector is sine squared t plus cosine squared t, the minus cancel out, plus 0 over square root of 2. The radical again simplifies to 1, and everything simplifies to 1 over 2. So notice that in this case, the curvature happens to be constant. Remember, in a full circle, I actually expected that. It's pretty easy to see. If you have a full circle, that the curvature is basically a constant, because it's the same turn with respect to the distance traveled. I'm going to show you with Maple in the last part of the class. The same is the case for this 3D curve, because it's a spiral, but the spiral expands linearly. That's the key thing. So if I were to sketch this thing, see x and y is sine of t, cosine of t, and t, right? So the curve itself was this. And that gives you basically a spiral, kind of hard to sketch by hand. Again, we'll do that with Maple. Let me try to do it kind of like that, right? But the idea is that because z is linear, the derivative of z is 1, which means that z expands at a linear rate. So you still have the same turn. I mean, you really visualize yourself traveling on the spiral. As you move with respect to x and y on a full circle, so x and y describe a full circle, the turning, the unit vector that indicates how much you turn, or t prime if you want, still has the same magnitude, because you go up at a linear rate. You go kind of to the left and upward at a linear rate. So that means there's no difference from one point to another with respect to how much you turn with as you move along the curve compared to how much you travel. All points are essentially the same. Now, before, if you had t squared over 2, like in the example I crossed out over here, that won't be the case because z expands faster, right? I mean, so therefore the distances between these spirals as you move around the z-axis will be larger and larger. So you could expect then the turn to be the amount of turn to differ from one point to another. Again, we'll talk about that in the last part with Maple. Let's do another example that involves the second part of the formula, and I think I'm gonna do it. Let me see the example itself. Yeah, let's just do it. Let's see. Yeah, I'm going to state it here and then repeat it on the second page. Maybe you can pause the video and try to do it on your own. Try to do it with the second version of the formula before I turn the page. So let's look at the vector function t squared e to the t, and I'm going to want the curvature at 1, at t equals 1, and the curvature at 5. What I like you to do, which is a very nice question very useful question to ask yourself. Before you compute anything, just look at the function here carefully. Could you guess which one is larger? K of 1 or K of 5? I claim that you should be able, if you understood and follow everything in this class so far, you should be able to tell which of the two is larger. Try to visualize the curve, roughly speaking. You don't have to have an exact picture in front of you. See how these functions differ, how they evolve as t, for example, goes from 0 to infinity. See if you can guess which one gives you a higher curvature, at 1 or at 5. So let's stay tuned for the answer on the second page. All right, so the answer to my question on the previous page is that k of 1 you should expect to be larger than k of 5. Okay, how do I know that? Well, let's look at the functions here, and then we're going to convince ourselves with the actual answer. Let's look at the curve of the components on the curve. E to the t goes to infinity much faster than t or t squared for that matter. So as t goes from 0 to infinity, these points go upward faster than they go around, with respect to x and y. So they move away from the origin, right? Because x and y are t and t squared. But z goes much faster, which means that the effect is like this curve is stretched vertically quite a lot as t increases. So if t increases even from 1 to 5, e to the 5 is so much bigger than e to the first. If I compute k of 10, for example, if t equals 10, it's even much larger pull. So that means this curve is basically nearly a straight line. The larger the t is. What does it mean? I mean, in terms of the curvature, nearly a straight line means very little turn corresponding to the distance traveled on the curve. So for any larger t, I should expect lower and lower curvatures at those points. And let's do the whole thing with this version of the formula. So r prime is 1 2t e to the t. R double prime is going to be 0 to e to the t. When you apply the formula, obviously plug in the point now, then you compute the cross products. Don't compute the cross products with t there because it's too tedious. So let's set up r prime of 1 cross r double prime of 1. Remember the formal determinant, the symbolic determinant. R prime of 1 will be 1 to n e, and then r double prime of 1 is 0 to e. All right, so we have the components 2e minus 2e, which is 0. Middle guy is minus e, and then 2. So that is the vector on the numerator. So therefore k of 1 is going to be the magnitude of this cross product over the magnitude of r prime of 1. R prime of 1 is 1 to e. So the magnitude of 1 to e to the power 3. So square root of e squared plus 4 on the top over square root of 1 plus 4 plus e squared to the power 3. Obviously use a calculator. This should be approximately 0.08. What about at 5? R prime of 5 cross R double prime of 5. That's going to be 1 10 e to the 5th. And then 0 2 e to the 5th. We're going to have 10 minus 2, 8 e to the 5th. Minus e to the 5th and 2, and the curvature at 5 is going to be the magnitude of this guy over the magnitude of r prime of 5, which is 1 10 e to the 5th to the power 3. Alright, so finally that gives me square root of 64 e to the 10 plus another e to the 10 plus 4 over 1 plus 100 e to the 10, all this to the power 3. Again, I did this before, ahead of time, obviously. I did it before, that's why I did it. I write the answer right away, but you should check on your own to convince yourself. Don't just trust my words. And by the way, if you see a typo, I'll be thankful if you actually write it in the comment, if there is a typo that squeezes in here. Anyway, 0.00036, obviously it's a much smaller number than as expected, than 0.08, right? So with that in mind, I think that is enough for today. We still have to go over another important concept, the concept of a normal and bionormal, and the so-called TNB's frame of reference. So I think, let's see, let me think a little bit if it's worth doing it on the second page or not. We're going to do it on the second page, the main thing, but let me give you just, so the last topic for today, we're going to talk about the so-called normal and binormal. So let's actually go over some preliminary stuff, and then we'll talk about what these are good for. Anyway. So we established, let's come up again with the tools related to the motion in space, right, on a curve. We talked about the tangent vector. Right? We already have some uses of it, right? Notice that the same thing can serve different purposes, right? This tells you the same tool serves to find the velocity. The same tool serves to find the speed, which is the magnitude of a tangent vector. If you put it in the integral, that gives you the arc length. So be aware that in different contexts, the same mathematical object, of course, can represent or can be used for different purposes. So related to the tangent vector, we defined the unit tangent vector. The unit tangent vector is, as the name implies, just the tangent normalized so that it has length 1. Why? Because you want a tool to encapsulate just the direction of motion. So if you care just about where you go, just where, not fast, how fast you go, then you're going to use the unit tangent vector. Now, also related to this, we have the derivative of the tangent vector. It tells you how much you turn, or the rate of change of this. Now, when I say how much you turn, notice that as a vector, that's not a unit vector, t prime of t, this tells you essentially where you turn and how fast. Remember, it has both a magnitude and a direction. Where you turn, how fast, because you just differentiated the unit tangent vector. Okay, so that vector that indicates the direction of motion. Just for the same reason that you actually normalize the tangent vector, you may want to normalize the derivative of the tangent vector if you just care about where you turn, just the direction of turning. Right? So unit tangent gives you just the direction where you go, irrespective of its magnitude, irrespective of the speed. A unit vector in the direction of t prime will give you just where you turn, in the indication of turning, not how fast you're turning. So that brings you to the concept of the normal vector, denoted by n bar of t, which is just the derivative of the unit tangent vector normalized so that it has length 1. People sometimes get confused here because they don't realize just by looking at it that essentially to achieve in computing the normal vector, you go through differentiating essentially twice the original function, right? Because to get the unit tangent, you have to differentiate r. To get the normal, you have to differentiate t, which, that's basically differentiated r prime again, you actually differentiate the whole fraction here, r prime over the magnitude of r prime, but you know what I'm talking about. So you basically end up differentiating the original function twice. So let's put this together. Unit tangent r prime over its magnitude, and that's it. I mean, we have it already here. I'm not going to write it again, right? So t of t r prime over its magnitude and t prime over its magnitude, t prime of t. This is the tangent and the normal. And let's see. Let's see if I do it here on the same page. Yeah, let's actually continue on the second page. I'm going to write this again to have them nicely on the top, and then we'll continue on the second page. All right, so I wrote down again these guys here. Leave some room on the top. I'm going to put, there's going to be another vector here that's important, the so-called binormal, that I'm going to add here on the top. Sometimes to save some time, I mean, I think I mentioned this before, you don't have to write of t all the time. If you know from the context that all of these are functions of t, you can just write it like that. Just be aware that these are functions of t. I want to go over a small computation here to notice the geometry of the unit tangent and the unit normal relative to each other, the geometry of them relative to each other. So, and that's also allows me to go over a couple of to review a couple of formulas related to vector computation. So notice that because the unit tangent, well, since it's called unit tangent, its magnitude is 1, right? Which means if I square the magnitude of unit tangent, that's going to be equal to 1. So that's by definition, well, the way we define it, right? Length of t is 1, therefore the length of t squared is 1. Now remember that the magnitude squared of any vector is related to the dot product. That is to say, the dot product of a vector to itself is the magnitude of that vector to the power 2. So magnitude of t squared is t dot t. These are functions of t on the left, so I can just differentiate both sides with respect to t. And if I use the chain, the product rule, which still applies, by the way, for the dot product, so we're going to have t prime of t dot t of t plus t of t dot t prime of t equal to 0. Now the dot product is commutative, so this is the same as saying 2t dot t prime is equal to 0, which is another way of saying that unit tangent dot t prime are equal to 0. Now, what did we learn about two vectors whose dot product is equal to 0, geometrically speaking? So I hope you remember that this means that t and t prime are perpendicular. They're orthogonal. But remember, the normal, the unit normal, is parallel to t prime, right? I mean, because unit normal is nothing but t prime normalized, right? It's a scale down to length 1. So that implies that the unit tangent and the unit normal are orthogonal. At any point on the curve, as you move along the curve, these vectors change. Remember, these are functions of t, but they're always perpendicular. So that leads us to the concept of a frame of reference that is basically local or centralized to the point in motion, with the origin at the point in motion. And to make it a true three-dimensional coordinate system, we need a third vector perpendicular to all of these guys. So we have t and n perpendicular to each other. How do we create another vector perpendicular to both t and n? And I hope you remember that the tool at our disposal is going to be the cross product. So this basically leads us to defining the so-called binormal, denoted by B, which by definition is equal to the cross product in this order. Remember, the order matters for the cross product between the unit tangent and the unit normal. So together, T, N, B form a frame of reference with the origin at the point in motion, and basically encapsulates the information related to the direction of motion. And it changes with the object, obviously. Let's do a little bit of a sketch here, and we'll talk about a couple of other concepts here. And again, I'll show you some images with Maple at the end. Make sure don't skip the last part. So let's say the motion is like that, the curve, and the point in question is here, and we're gonna have, let's say, the tangent vector with let me actually do the curve with the black color. Oh, sorry, got to change the color. All right, and let's do, I don't know, let's say the tangent is with red, the unit tangent. So suppose the unit tangent is over here. Let's do the normal with blue. And try to visualize this in space, right? Kind of like, imagine this is kind of on the left from your perspective and going toward the page here. And if you remember the right hand rule, right, for the orientation of the cross product, this is the normal here, not the binormal. This is n, the normal. So the binormal will be perpendicular to both t and n, and let's say it's here. Okay, right? So any two pairs are perpendicular to each other, right? So they form this frame of reference. So again, just to recap, T indicates where you go. N indicates where you turn. What does B indicate? Well, it has different uses, but the most intuitive one I can tell you is that if you imagine that you go, as an analogy, imagine that you move on the curve, or an airplane or something like that, B keeps track of the direction toes to head. And in other words, for example, the direction of B is always keeping track of the original up, if you want. Okay, so you walk on the curve, depending on how n changes. Like for example, you may have a twist, right? If you turn in such a way that you have a twist on the curve, then B keeps track of the direction of a straight from toes to head. Now, B also has other uses because, for example, in combination with other vectors, they form planes with might be some important properties. So for example, together T, the plane made by T and N, this is also called the osculating plane, which is basically the closest plane to the curve. So local to that point in question, the closest plane to that curve is made of these two vectors, T and N, the tangent and the normal. The N and B together form what is called the normal plane. The normal plane, basically, it's the curve is basically nearly perpendicular, of course, to that plane. It's like emanating perpendicular from that plane. forms a plane that is, I mean, if you approximate the curve with a line close to the point in question, that plane is perpendicular to the curve, which is the reason it's called a normal plane. So let's finish up this I think a little bit. Finish up this section, this lecture with an example or two. Yeah, let's just do an example. And I'm going to go over some other examples on the last part with Maple. So I'm going to do an example which is a little bit more tedious, just to point out that this stuff can be tedious if you do it by hand, but I'll do just one just for the sake of it. And usually, like I said before, in quizzes or exams, I'll keep that in mind and, you know, have easier numbers to deal with. And I'll show you how to do that in Maple much faster. So let's compute these vectors for the following curve: t squared over 2 and t squared. All right, so let's start with r prime of t. That's going to be 1t and 2t. Now it's time to do the unit tangent. For that, I need the magnitude of r prime, which is square root of 1 plus t squared plus 4t squared. That's going to be 1 plus 5t squared. So therefore, the unit tangent, this is where it's very useful to keep these scalars out, not inside the vector. So the unit tangent becomes 1 over the magnitude, scalar multiple with 1t and 2t. Because if you keep it the scalar out, now when the painful part comes to differentiate t in preparation to compute the normal, then you're going to do one product rule instead of 3 of them. Okay, so to compute the normal, we need t prime first. Let's prepare this piece here. So 1 plus 5t squared, 1 over that, that's like 1 plus 5t squared to the minus 1/2, because we're gonna do the power rule there, right? So the derivative will be the product rule, 1 plus 5t squared to the minus 3/2. Let's see. I forgot the minus 1/2 in front of it. I'll put it here. So minus 1/2, 1 plus 5t squared to the minus 1/2 minus 1, which is minus 3/2. The chain rule now followed by 10t, and then the vector 1t and 2t. Plus, now we continue the product rule, 1 plus 5t squared to the minus 1/2. Scalar multiple with the derivative of that vector, which is 0, 1, 2, right? 0, 1, and 2. Okay, now, how do we simplify this a little bit? Well, just pull out this parenthesis with the smaller power. So if I pull out, let's see, t prime, I'm going to pull out 1 plus 5t squared to the minus 3/2. You should probably pause and do this slower on your own. And if I pull this out, the remaining part, I'm going to bring it in a single vector here. See, these two, minus 1/2, 10t, this becomes minus 5t. Scalar multiple with that vector, that's going to be minus 5t, minus 5t squared, minus 10t squared. Like that. And in the second part, since I pull minus 3/2, there is a copy of 1 plus 5t squared still remaining. So that's going to be 0, 1 plus 5t squared, 2 plus 10t squared. I brought it inside the vector 0, 1, 2. All right, let's see if we get something more humane here. If we add up this together, so t prime is going to be 1 plus 5t squared to the minus 3 halves, and then together the vector becomes minus 5t squared cancels, so that's 1 and then 2. So that's just t prime. We have to normalize it, that is to say we have to divide it to its length. So we need to produce, we're going to use the second page obviously, we need to compute the magnitude of this. I want to point a little bit how useful it is to be careful how you go over this if you have to do it by hand, and how advantageous it is to keep the scalar out if possible. Because for example, the magnitude of a scalar product is going to be the scalar out, 1 plus 5t squared to the minus 3 halves, times the magnitude of the remaining vector, which is in this case 25t squared plus 1 plus 4, which is plus 5. We're going to simplify this further on the second page, so stay tuned. Okay, so I copied from the previous page t prime and its magnitude. Finally, let's set up the normal. By the way, in case you get desperate with this example, I don't do it more than once, even in classroom, right? I feel like at least once we should do a tedious example, and then we can rely with Maple. But for once, because you never know when you actually have to do it on paper, so you need to handle this if push comes to shove, even if it takes longer time. So n of t is t prime over its magnitude, right? So t prime over the magnitude. Let's put these together. So 1 plus 5t squared to the minus 3 halves minus 5t 1, 2. And then on the bottom here, let's see if we can simplify this somehow. I think I'm going to have to check this. Let's see. T prime. Yeah, I forgot minus 3 over 2 here. Sorry. All right, this guy actually cancels. Square root of 5 plus 25t squared. Anyway, these scalar that I kept out, now they cancel, so therefore the unit normal is 1 over square root of 5 plus 25t squared, scalar multiple with minus 5t, 1 and 2. You can actually check to see that its magnitude is indeed 1 as expected. Okay, so let's relax a little bit. I'm not going to compute the binormal in terms of t. That's going to be too much of a detour. It'll make the video too long as it is. But here, the remark that I want to point out here. Let's say that the original problem is to actually compute these vectors at 0. Always remember to plug in t with whatever value you have to compute as soon as possible. Now obviously you need to do that after computing the derivatives. After all the derivatives that needs to be computed are computed. So in this case, for example, the binormal, we don't need to do it in terms of t. I can just go back to the, we have it in the previous page, t of 0, the unit vector, t of 0 is going to be actually 1, 0, 0. We have it in the previous page. The normal at 0 is going to be 1 over root 5 scalar multiple with 0, 1, 2. I can put it inside now because I need to prepare it for the cross product. And the binormal then at 0 by definition is the cross product of these guys. So remember, if you have to do it at a specific point, you do not need to do it in terms of t when it comes to compute the binormal. Just plug in the point and then do the cross product, which of course is much easier. So what do we get here? The first component is 0, then minus 2 over root 5, and 1 over root 5. So in this case, the binormal happens to be a, yeah, so the binormal at 0 is given by this. Okay, so I think that is enough for the written part. Make sure you watch the second part, because the images obviously and the pictures will be much better, much more suggestive in Maple than what we did on paper. I'll see you next time.